Hi, I'm Sean Moran with ACC GIS, and our topic today is 3D data. Now, I want to kick off our discussion by introducing you to a concept known as geodesign, which uses GIS to bring geographic analysis into the design process. Now, geodesign sounds like a fancy new term, but it comes from a book published by Ian McHarg in 1969 called Design with Nature, in which he described a process by which environmental data could be incorporated into the planning process. And he's the one who popularized the process of overlaying spatial data to support design, analysis, and presentation. And so not only did he forward the concepts on which geodesign is based, it's also those same concepts of which GIS is founded on. And if you look at the example on the right, you can see the cover of Design with Nature, along with a page that includes hand-drawn maps of the same extent with data overlaid on top of each other. Now, geodesign is a process, not a tool. It uses GIS to integrate 3D physical, natural, and administrative models into the design process, where architects, engineers, geographers, and planners work with stakeholders like staff, public officials, political leaders, and the public to collaborate on a plan that works for everyone involved. Here's a diagram of the traditional planning process, which is very linear, and all of the participants' roles are very compartmentalized. It has a conceptual, planning, and detailed phase that generate a concept level, plan level, and detail level development scenario. Now, the stakeholder input happens at the very beginning of this process in the conceptual phase, which you go out and you meet with your local and political officials and the public to get their input into the concept. At that point, it gets handed off to the planners who develop the plan level document, and then that gets handed off to the architects and engineers who develop the detailed level development scenario. The stakeholders don't get to see the results of their process till the very end when it comes out. And at that point, there's not really an opportunity to change the plan at all. And so it often generates a lot of opposition to the resulting detailed level development scenario. Now, back in 2014, I worked as a contractor with Civic Analytics and Nathan Brigman to introduce geodesign into a traditional planning process. And we had been contracted out by the University of Texas and the city of Austin on a master planning effort to redevelop a 208-acre city of Austin owned site known as Colony Park. And what you see on your screen there are development scenarios that traditionally come out of the conceptual phase of the planning process. Now, the large image on your screen includes the Five Hills development scenario, in which blue buildings are existing buildings, green is open space, red is proposed commercial, orange is proposed multifamily, and yellow is proposed single family, along with a network of streets and amenities to support the development. And there were three different scenarios that came out of this conceptual phase. And just as they were wrapping up this phase, the city of Austin brought in myself, Nathan Brigman, and Civic Analytics to introduce geodesign into this process. And so while the traditional planning process is linear and compartmentalized, when we add in geodesign, it becomes iterative and collaborative. You can see the traditional planning process diagrammed on your screen there, but between the conceptual and the planning phase, while still working with the stakeholders, we've introduced some tenets of geodesign, including geomodels that allow us to visualize in 3D what the proposed development might look like, fast feedback. So we're not only getting visual feedback, but we're actually quantifying the results. What does this development mean for population, for parking, for taxable value, for open space? And because we're doing this within a geographic information system, it allows for very low cost sketching and iterations while we get that feedback from our stakeholders. So when we get to the end of the process, when the architects and engineers deliver the detailed level development scenario, the public has already bought into what this process means to their community. So here we are back in the Colony Park master planning effort, but this time we're armed with geodesign. And so we took the traditional planning documents, digitized those into GIS, and envisioned them with geomodels and created these 3D scenarios in which stakeholders could interact with each of the scenarios. We also linked the 3D models to a spreadsheet scenario development tool called Envision Tomorrow, in which we can compare the metrics for each of the different development scenarios. And of course, this involved GIS and spreadsheets, and so it allowed for sketching and iteration. You can explore these different 3D geodesign scenarios yourself by going to a web browser and searching for ArcGIS Online. And in the search toolbar, search for Colony Park. And there you can see the 3 items that list the Colony Park Blue Stem, Five Hills, and Moonrise development scenarios. And the idea is that you could click on each of these, interact with them, and then provide feedback into the scenario development process. Now, if we click on the Colony Park Blue Stem scenario, it opens up the City Engine web viewer, which allows your stakeholders without any GIS software to interact with the 3D development scenario. And so you can see how we converted the 2D drawn sites into a 3D model for them to interact and explore. There I'm changing the perspective to 3D. And zooming in the backyard of a neighbor so we can see what the development scenario might look like from their perspective. Of course, this is a GIS. So not only do I have the 3D geographic features, but I can click on a feature and bring up the attributes associated with it. In this case, it's the quantified metrics that we developed in the Envision Tomorrow sustainability model. Now, if we return to ArcGIS Online, you can see that the power is not only interacting with one of the scenarios, but also being able to compare scenarios. And so I can bring up 2 scenarios, for example, side by side, and see the different master plans visualized in 3D. Now, geodesign is just one of the many applications we'll discuss when learning about 3D data today. But first, let's start with the performance criteria for this topic. By the end of this topic, you'll be able to explain how z-values are located in a vertical coordinate system. You'll be able to describe the triangulated data model, structure, and associated attributes. You'll be able to list the advantages and disadvantages of the triangulated data model. And you'll be able to list and compare 2D, 2.5D, and 3D data types. Last, in the demonstration and project, you'll create a triangulated irregular network and a geodatabase terrain in GIS. Why 3D? There are some unique advantages of three-dimensional GIS. We see in 3D, and 3D allows us to visualize the world in GIS. We live in 3D. It's very intuitive to us. And so if we can present our data in 3D, it makes it intuitive as well. And last, we interact in 3D. And so it creates for a very immersive three-dimensional experience in GIS. And if you look at the image at the bottom of your screen, you can see a prototype of an augmented reality driver assisting technology that is projected on the windshield of the vehicle. And so it's very visual. All of the information that you need as the driver is right there at your disposal, including your speed, the safe track that you need to follow, directions, and maybe how much gas you have. So you never have to take your eyes off the road. It's very intuitive. We don't need a manual to understand what it's telling us. And of course, because if it's presented in augmented reality, it's very immersive. I can interact with the world in my 3D GIS data at the same time. There are a number of industries that are employing 3D data analysis and visualization. We've already talked about planning and how they use it for scenario planning, but also the design community utilizes it to design individual utility and civil infrastructure projects and get feedback on those. The construction industry utilizes 3D data not only to design a new building, but to manage the construction and then pass on that data to the building manager to maintain the building as well. That's called BIM, or Building Information Management. We also see 3D data employed in science-based industries like oceanography, climatology, and geoscience. These all have three-dimensional physical components to the world in which they are studying. In the example on the left, oceanography, this is a study in Monterey Bay that is looking at the oxygen level of the ocean over time. Of course, the climate is a very three-dimensional world, and we can use 3D GIS to analyze and visualize what's happening to our climate. And then, of course, geoscience utilizes 3D GIS to look at the subsurface environment, fault lines, geologic formations, potential energy production, volcanic activity. 3D GIS allows us to study and understand this data in a way that wouldn't be possible in a 2D environment. Other industries employing 3D data analysis and visualization include aviation, disaster response, and military. Aviation is a very complex 3D problem where you have all of these independent objects, airplanes moving through both restricted corridors and zones designed by the FAA. All of this is three-dimensional. In disaster response, you can imagine in this example right here, we're modeling a spill at a petrochemical plant and then working with staff and emergency responders on how to address the spill. And this is a really cool example of how the military might utilize 3D data. You can imagine that a single weapon system might cost $500,000. And so to train a soldier on it is very expensive. In this case, they're utilizing augmented reality to train these soldiers on these expensive weapon systems. So not only are they saving money, but when they go in the field, they'll be better prepared. We're even using 3D GIS to support space exploration. This is an example of a 3D model that NASA has produced and you can interact with via your web browser online. This is the 2D presentation, like when you first open up ArcGIS Pro, but we can convert it to 3D. And there you can see Mars in 3D. And I can interact with it by zooming in and zooming out and spinning the globe to find a particular area that I might be interested in. I can even list areas of interest. There's the Curiosity landing site. I can learn about it. And then when I'm ready, I just click on the Fly to Area button and it'll zoom in on this site and I can interact with it in 3D. And so there I can see that it's a pretty flat area where this space vehicle landed, but it's within a pretty dramatic valley on Mars. And so you can see how 3D data and interacting with it goes way beyond what we can do with two-dimensional data. So let's back this discussion up all the way to the beginning, which are z-values. Up to this point, we've been using 2D data in this class, and 2D data is flat. It's represented by horizontal coordinates, an X and a Y that might represent, for example, latitude and longitude. And if you look at the diagram on the right, you can see I have an X-axis and a Y-axis, and the shadows of our data points are plotted in 2D on these X and Y axes. Now, 3D data has depth, and it's represented by not just horizontal, but vertical coordinates as well. In this case, a z-value, and the z-value might be elevation, or it can also be something like precipitation, population, and crime. If we look back at our example on the right, we can see we've added a z-axis, and now we're plotting the points not only in horizontal space, but also in vertical space as well. And the z-value of each point determines how high in the vertical space it's plotted. In this case, 250 is higher than 150, and 150, of course, is higher than 50. Where we actually plot the z-values depends on the z-axis, which is defined by the vertical coordinate system, and it includes a vertical datum, a linear unit of measurement, and a direction. So to this point, we've only used horizontal coordinate systems. But when working in 3D, we also should use a vertical coordinate system that first defines the zero elevation to which heights are referenced. That's the datum. And the most common vertical coordinate system that we utilize in the United States is NAVD88, or North American Vertical Datum 88, which is referenced to mean sea level. That's the datum at Quebec, Canada. That's 0. Now, vertical coordinate systems also include a linear unit of measurement, which is always feet or meters, and the direction as well. A height-based vertical coordinate system is considered positive up, and a depth-based vertical coordinate system is considered positive down. And if you look at the left side of the diagram, we have a height-based positive up vertical coordinate system in which the base of the z-axis starts at the datum. In this case, it's the mean sea level. And then, of course, it's a height-based positive up. So as we increase in height, our z-value also increases. On the right side of that diagram, we have a depth-based positive down vertical coordinate system. This time, the datum is defined by the mean low water level. That's the 0 level. And then as we increase in depth, the z-value increases as well. Now, for most of the three-dimensional work that we do, we utilize height-based positive up vertical coordinate systems. But if you were working in oceanography, you might utilize a depth-based positive down vertical coordinate system.